As told at the end of the last lecture, we shall continue our discussion on displacement analysis of planar mechanisms using graphical method. Last time we had examples, 3 examples, all were 6-link mechanisms with single degree of freedom. Today we shall discuss or take up a little more involved mechanisms with more number of links and maybe with more number of degrees of freedom, and show how the graphical method can be used for displacement analysis. As the first example today, that is the 4th example in the overall displacement analysis, we consider a 9-link front-end loader. First, let us have a look at the model of this loader. To start with, let us first discuss the model of this mechanism which is used for a front-end loader. As we see, there are 2 hydraulic actuators between link number 2 and link number 3, and there is another hydraulic actuator between this red link and this link, that is link 6 and link 7. By moving these 2 hydraulic actuators, we can move the front end of this loader, that is this bin, which is link number 9. We will first show that this particular mechanism has 2 degrees of freedom and with 2 inputs here and there through these 2 hydraulic actuators. Consequently, this output link cannot go anywhere with any arbitrary orientation. It will have only 2 independent coordinates which you can specify, either the xy coordinates of a point on it and the orientation will be automatically fixed up, or only the x coordinate and the orientation of this bin and the y coordinate will be automatically decided. So let us now determine the displacement analysis of such a mechanism by graphical method. That will be our next example. Let us now discuss the problem of displacement analysis with reference to this front-end loader, the model of which we have just now seen. As we see, there are 2 hydraulic actuators, one at Z1, one named Z1 and the other named Z2. Link number 1 is the body of the truck, and this hydraulic piston cylinder constitutes link 2 and link 3. There is obviously a prismatic pair between link 2 and 3, which is the piston and the cylinder. Similarly, there is a prismatic pair between link 6 and link 7, where there is a hydraulic actuator, again between the piston and cylinder of this hydraulic actuator. Link 7, one end is connected to this body of the truck at the revolute pair at O7. Link 4, one end is connected to a revolute pair to the body of the truck O4, and link 2, one end is connected to the body of the truck by a revolute pair at O2. Now let us see, this mechanism does not have all binary links as we have considered earlier. All the first 3 examples that we considered, they had either binary link or ternary link. Here, if we consider link number 4, as we see, it is connected to 4 different links, namely to link 1 at O4, link 3 at A, link 5 at B, and link 9 at C. So link 4, which has 4 revolute pairs, becomes a quaternary link, and link 5 is a ternary link connected to link 8, link 4 and link 6, and link 9 is the front end of the loader, that is the bin. So in this mechanism, because we have a quaternary link, that is a very higher order link, I will show how to conveniently use the tracing paper as an overlay, as we discussed in the previous lecture. Now let me state the problem. The problem is posed as follows, that if link number 9, the point D of link number 9 comes to D prime. This is the scale of the drawing 25 centimeters is represented by this distance. Now, when the point D comes to D prime, can we locate all other revolute pairs? That means, where do they move in this configuration when point D of link 9 has moved to D prime? Before that, let me show that this mechanism has 2 degrees of freedom. For that, we count the number of links n, which we, as you have seen, 1, 2, 3, 4, 5, 6, 7, 8 and 9. N is 9. Now, let me count the revolute pairs and prismatic pairs, that is J, the number of joints. What we see? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 revolute pairs plus 2 prismatic pairs, that is at these 2 hydraulic actuators. So, total J is 9 plus 2, that is 11. If we remember our formula to calculate the degrees of freedom, that is F is equal to 3 times n minus 1 minus 2j, which we get 3 into 8 24 minus 2 into 11 22, that is F is equal to 2. Thus, it is a 2 degrees of freedom mechanism. Because we have 2 independent inputs at these 2 hydraulic actuators, it is a constant mechanism. Because it is 2 degrees of freedom, I can have 2 degrees of freedom for this output bin, that is, the point D can go to D prime, but at that location the orientation of the bin will be automatically determined. I cannot take D to D prime and then again change the orientation. So, we will solve this problem, that when D goes to D prime, how do we determine the location of all other revolute pairs? That is the first part of the problem. This is the figure of the same front end loader which we are discussing right now. As I said earlier, the point D has moved to this point which I call D1, and the objective is to find the location of all other movable revolute pairs, that is at A, B, E, F and C. We should note that O4C being 2 revolute pairs on the same rigid link 4, the distance O4C cannot change. So, C must move on a circular path with O4 as center and O4C as radius. So, this is the circle on which C must move. Also, D and C being 2 points on the same rigid link, that is number 9, that is the bin, this distance also cannot change. Because I know the location of D prime, I put my center of a circle with DC as radius with D1 as the center. If I draw this circular arc, C must lie on this circle. Thus, we get that C should lie on this circle and also on this circle. That means the intersection of these 2 circles determine the location of C. When D moves to D1, C moves to C1. Now, to locate the positions of the hinges, say A and B, which lie on link 4. As we noted earlier, link 4 is a rigid link, but it is a quaternary link having 4 hinges, one at O4, other at A, other at B and one at C. Now, we know when D comes to D1, C has moved to C1. O4 does not move, so O4 remains there. To locate the positions of A and B corresponding to the second position, what we do, we take a tracing paper and mark these points O4, A, B and C. The relative positions of these O4, A, B, C can never change because they lie on the same rigid body. So, what I do, I move this tracing paper now with O4 at O4 and C at C1. So these two red dots, which are the positions of A and B, is automatically determined A and B move to these new locations. So if we can now pierce this tracing paper here and there, I immediately get the locations of A and B. This point will give me A1 and this point will give me the location B1. Let me repeat it once more. Because O4, A, B, C are 4 points on the same rigid link, I use this tracing paper as an overlay, mark the relative locations of O4, A, B and C. Because 2 points define the rigid body completely, and in the second position I know the location of O4 and the location of C1. So I take these two red dots corresponding to O4 and C to this new location, and wherever these two dots come, they are the positions of A and B corresponding to the second configuration. Now, once we have obtained D1 and B1, it is very easy to determine the new location of this revolute pair E, because the distance DE does not change. So with D1 as center, I draw a circular arc with DE as the radius. So E must lie on this circle, and BE also does not change. So with B1 as center, I draw another circular arc with BE as the radius. Wherever these two circles intersect, that gives me the location of E, which I call E1. Similarly, to determine F, I know the locations B, E and F. These are the 3 points on the same rigid link 5. So I can again use this tracing paper as an overlay and mark B, F and E. Their relative positions do not change, and I know where B and E has gone. So I can replace this, coinciding this B with B1, this E with E1, and wherever F goes, that becomes the location of F, which I call F1. So I have determined the location of all the moving hinges, namely A, B, F, E, D, as A1, B1, E1, F1, and D1 of course was given, and C as C1. So we have solved this part of the problem, that corresponding to the second position when D has moved to D1, where all other moving hinges go. Not only that, I can also find what is the inclination of the bin from the first position. That is, this line CD, that was its initial orientation, has now become this. So angle between these two lines, CD and C1 D1, determines the change in orientation of the bin. If I draw a parallel line through D1, let's say this is the line which is parallel to CD, then this amount of counterclockwise rotation of the bin has taken place when D has moved to D1. The problem that we have just solved, let me now restate the problem for your benefit. This was our example 4. The first part of the problem that we have just solved is that determine the location of all the revolute pairs when the pair at D moves to D1. We have also found out what is the amount of rotation of the bin corresponding to this movement. Now I leave an assignment for you to do from the same figure. Assume the actuator Z1 is held fixed, that is, the distance O2A is not changing, and the actuator Z2 is activated to change the distance O7F in the figure to 3/4 of its present value, then what will be the corresponding rotation of the bin? You can follow exactly the same logic and same technique of graphical analysis to solve the second part of the problem. Let me now go to another example, which is our example 5. Now I will show you a figure which will be a simple 3R1P mechanism to scale. First we will verify that this is a non-Grashof type linkage. That means all the links can have only angular oscillation, no link can rotate completely. The problem will be to determine the ranges of oscillation of these of links 2 and 4 in this particular non-Grashof 3R1P mechanism. Let me now show the figure of this problem and solve the problem for you. Let us now consider this 3R1P mechanism. As we see, link number 2 has a revolute pair with link number 1 at O2 and a revolute pair at A with link number 3. And link number 3 has a prismatic pair with link number 4. And link number 4 has a revolute pair at O4 with link number 1. So in this revolute 3R1P mechanism, there are 3 revolute pairs at O2, A and O4, and there is a prismatic pair between link 3 and link 4 in this direction. So first of all, let us identify what are the kinematic dimensions of this 3R1P mechanism. O2, O4, that is one link length, let me call it L max, and O2A is another link length which is L2, let me call it L min. This 3R1P mechanism has only one more kinematic dimension, that is the offset. One should not be confused by this dimension. This dimension has no kinematic significance because the location of this revolute pair A I cannot change, but the prismatic pair between 3 and 4, which is along this direction, I could have drawn it through A. This is the prismatic pair direction, and this perpendicular distance from O2 up to this direction of the prismatic pair, that is the other kinematic dimension E, which we call offset. If we measure this L min and E, we will find that L min plus E is greater than L max. Consequently, this will be a non-Grashof 3R1P chain and no link will be able to rotate completely, all links will be oscillatory. The question that is asked is, find the angle through which link number 2 and link number 4 can oscillate. Let me repeat, it is this distance which is a red herring, which is there only to confuse you, because it is the location of the revolute pair O2, O4 and A I cannot change, and prismatic pair has no location, it is only a direction that is marked by this line. So I draw a line through A parallel to this direction of prismatic pair and get the kinematic diagram for this particular linkage. Let me now solve this problem to determine the angle through which links 2 and 4 can oscillate. Let us consider now the kinematic diagram of the 3R1P mechanism we are discussing. This O2, O4, that is what we call L max, O2A, that is what we call L min, and the perpendicular distance of O4 from the direction of sliding passing through A is what we call the offset E. By measurement we can find that L min plus E is more than L max. So it is a 3R1P non-Grashof chain, and we have to find the angle through which the link O2A and link 4, that is this line, can oscillate. To solve this problem, let us imagine the equivalent 4R mechanism. That is, the prismatic pair between link 3 and 4 in this direction, let us replace it by a revolute pair at infinity in a direction perpendicular to this direction of sliding. That is, the hinge B of the O2A BO4, which is the equivalent 4R linkage, B is on this line at infinity. All parallel lines meet at infinity, so I can take any line perpendicular to the direction of sliding and claim that B is at infinity on any of these parallel lines, because all these parallel lines meet at infinity. Now, to find the extreme position of link 2 or link 4, what I know, the other two links, that is, say for extreme position of link 4, link 2 and link 3, that is O2A and AB, must be collinear. And A must move on this circle, which is centered at O2, and radius O2A. This is the path of A. We call it KA. And this offset E, this distance rotate with O4 as center and E as the radius, that is, this corner moves on this circle. Now, let me draw a common tangent to these two circles, one centered at O2 and the other centered at O4. The common tangent between these two circles are these two lines. This is one circle centered at O4, and this is the other circle centered at O2, with O2 as a radius. So, these two lines represent the common tangent to these two circles. Let me see what happens when A occupies rather this point, if I call it B prime. B is at infinity, I call this point B prime. When B prime comes here and if it oscillates in this direction up to this point of tangency, let me call it B2 prime. Let me find where is A now. These are the extreme positions of link 4, because as we will see, O2A and AB has become collinear now, because A is here, which I call A prime, and A is here, which I call A double prime. So, O2A prime, because it is tangent, is perpendicular to this direction of sliding, and B is also at infinity to this direction of sliding. So, O2A prime and B at infinity has become collinear. Same is true for the other configuration, O2A double prime and B, which is perpendicular to this line, direction of sliding, has become collinear. Consequently, link 4 has taken its extreme positions. So, this is the angle through which link 4 oscillates, where O4B prime is tangent, common tangent I have drawn, and this is the point of tangency. This is the common tangent to these two circles. This is the point of tangency. To find the extreme position of link 2, I have to say that O4 B prime and B prime B should become collinear. These two circles intersect at, say, this I call A triple prime and this as A 4 primes. Now B is moving on this circle, so B prime is also here. This point has moved to here, and O4, if I join this, the B goes to infinity in this direction, because B will be always perpendicular to the direction of sliding at infinity. So what we see, that this link 4 O4 B prime and link 3 AB prime have become collinear, and consequently link 2 has taken its extreme position. Same will be true for this point of intersection, and link 2 oscillates through this large angle between its extreme positions. Just now we have seen a very large angle of oscillations of the input and output links of a 3R1P mechanism, which is of non-Grashof type. Here is a model which is again a 3R1P mechanism, and this is the L min, this is the L max, and E is such that L min plus E is more than L max. Consequently, this becomes a 3R1P non-Grashof type linkage. Let us now observe the angle of oscillations of this link and this link. This is that common tangent that I was trying to draw between those two circles. This line is parallel to that common tangent, and consequently this has reached its extreme position. It cannot be further inclined. However, this link can still go, and as you see from this extreme position, it is returning, that is, it is rotating counterclockwise, though this link is still going clockwise. And this is the extreme position of this link, and now it cannot go any further, it has to return. Again it has reached that extreme position and it cannot go any further, but this link can go, and that will, yes, this is the extreme position, it cannot go any further, and this link can still go, and the red link starts rotating in the opposite direction. This is the extreme position of this link, whereas this is the extreme position of this link. From this has to rotate in this direction, it cannot go any further. And from this it cannot go any further, it has to rotate in the opposite direction from here. So for this 3R1P non-Grashof type linkage, as we see, it is a very complicated movement with a very large angle of oscillation for both link number 2 and link number 4. As the last example of displacement analysis, let us now consider a really complicated problem as shown in this figure. This is the figure of an earth-moving machinery, the model of which we have seen earlier. This particular machine has 3 hydraulic actuators, one at Z1, other at Z2, and the third one at Z3. So, this has 3 independent inputs. If we count the number of links in this mechanism, I will get n equal to 12. This will be clear when we draw the kinematic diagram of this particular machinery. If we count the number of pairs, we will see there are 12 revolute pairs and 3 prismatic pairs. So, J is 15. Consequently, if we calculate the degrees of freedom of this mechanism, F equal to 3 into n minus 1 minus 2J, we get 33 minus 30, that is 3. So, it is a 3 degree of freedom mechanism with 3 independent inputs. Consequently, it is a constant mechanism, and because of 3 degrees of freedom and with 3 inputs, this bin, that is the output link, which is defined completely by these two hinges J and K, can be taken anywhere with any orientation. That means I can independently take J to say J2 and K to another position K2, which will completely define the position and orientation of this output link, which is the bin. Second thing to note is that there is a very high order link which is connecting at C, D, E, H and K. That means this particular link has 5 revolute pairs in it, and it is a link of 5th order. So, we will show how we can use the tracing paper very conveniently to locate the revolute pairs in this kind of higher order link. Let me now solve this problem, that when J and K moves to J2 and K2 respectively, how can you locate the all other moving revolute pairs, that is at B, C, D, F, H and G and A. That is the problem that we will solve right now. So, now let us consider the kinematic diagram of this earth moving machinery which we have just seen. As we have said, there are 12 links, and this is the kinematic diagram, out of which link 3, as we see, have 4 hinges on it, O4, A, B, D. So, it is a quaternary link. Link 7 has 5 hinges on it, C, D, E, H and K. So, this is a link of 5th order. The question is, when these J and K move to J2 and K2, can we locate the corresponding positions of all other revolute pairs? To solve this problem, first we note that the point D, because O4D never changes and O4 is a fixed point, this D point must move on this circle with O4 as center and O4D as radius. It must move on this circle. So, D2 must lie on this line. Let me call it KD. Now, when K has gone to K2, but the distance KD also does not change. So, I measure this KD, and from K2 I draw a circular arc with KD as radius. So, D must move on this circle and also the circle drawn earlier through D with O4 as center. So, these two circles, one point of intersection is here, so I locate D2. Once I have located 2 points, that is O4 and D2 on this quaternary link number 3, A and B I can easily determine using the tracing paper. So, on a tracing paper I mark O4, A, B and D. These 4 points, their relative positions do not change because they belong to the same rigid link 3. Now, O4 does not move, so it stays here. When D goes to D2 and O4 stays at O4, wherever these two dots move, they define the location of A2 and B2. We have also located the points K which has gone to K2 and the point D which has gone to D2. Now, link number 7 is a link of order 5 and it has 5 hinges, namely K, H, E, D and C. Now, these 5 points do not change their relative positions, but K has gone to K2 and D has gone to D2. So, if I now take, this is K. So, K goes to K2 and let me mark this point, that will be easy to remember. This is K and this is D. So, when K goes to K2 and D goes to D2, K has gone to K2 and D has gone to D2, and these other marked points give you the location of C2, E2 and H2 and okay, there are 5 points K, H, E, D and C. I get K2, C2, D2, E2 and H2. So, once I have determined all these points, rest of the problem is trivial because these distances Gj and Hg do not change. If I know J which has gone to J2, H I have located, so I can easily locate G2 by Jg and Hg, these two link lengths. Rest of the points I leave for the students to complete. What we have demonstrated that the use of tracing paper is very convenient when you have such higher order links, and the displacement analysis can be completed if the problem is well posed. Let me now state the problem that we have just solved, which was our example number 6. In example 6, we had the figure which had the kinematic diagram of an earth moving machinery consisting of 12 links and 3 inputs, which are those 3 hydraulic actuators Z1, Z2, Z3. And statement of the problem was, determine the location of all the moving revolute pairs corresponding to configuration 2 when the hinges J and K occupy respectively the locations J2 and K2. I can extend this problem for you to have some practice, which are a little tougher. The second part of the problem could be, the range of movements of the actuators Z1 and Z2 are such that the maximum distance between O2 and A, that is O2A max, is say 1800 millimeter to the scale and O2A minimum is 1100 millimeter. Similarly, the movement of the actuator Z2 is such that the maximum distance between C and B, CB max, is 2400 millimeter and minimum CB is 1500 millimeter. The question is, determine the zone in which the hinge K lies when the full ranges of movements of Z1 and Z2 are utilized. The third part of the problem could be, determine the maximum tilt angle alpha of the bin while keeping the lip of the bin L at the location L2. As I said, I will not solve these problems in detail, just leave you with a little bit of hints. If we look carefully at the original diagram, what you can see that this distance O4A never changes because they belong to the same rigid body. Consequently, A lies on a circle with O4 as center and O4A as radius. The maximum distance between O2 and A, which is given to us, locates this point. Minimum distance between O2 and A, which is again specified in the problem, locates this point. So, I can locate position of A for the extreme movements of this actuator Z1. O4, A, B and D, all 4 belong to the same rigid body. So, using the tracing paper technique that we have just now seen, I can locate the corresponding position of D as D prime and D2 prime. For the extreme positions, one can see that link 4 and link 7 get rigidly connected and the distance DC also does not change. So, corresponding to the maximum position of DC and minimum position of DC, depending on the movement of the actuator Z2 corresponding to D2 prime, I get two locations for C. Same way, corresponding to D prime, I get two locations of C corresponding to the maximum and minimum distance of BC. Now, DCK, they belong to the same rigid link. So, corresponding to the DC, I can locate corresponding positions of K here and here. Same way, corresponding to D prime, I get the extreme positions of K as this one and this one. Now, the question is, what is the range in which the hinge K lies when the maximum movements of these two actuators between O2 and A and between B and C is utilized? This is the maximum distance BC, this is the minimum distance BC. One can easily see that when the two actuators have taken the extremum positions, the distance dk does not change. Consequently, this is a circular arc with D double prime as the center and this as the radius. Same way, this as the radius. So, I get these two circular arcs. Same way, one can say that distance from O4 does not change, again because if the actuators are at maximum locations, link number 4 and 7 get rigidly connected and K moves on a circle with O4 as center. So, this is another circular arc joining K1 double prime and K1 prime with O4 as center, and another circular arc with O4 as center and radius O4 K2 prime. So, these four circular arcs determine the region in which the hinge K can lie when the maximum and minimum distance between O2 and A and B and C are utilized by the hydraulic actuators. So, in the full range of operation, the hinge K lies within this region. With this hint, you should be able to complete the problem. To answer the third part of the problem, that is the tilt angle of the bin when the lip is kept at this location L2, we solve it as follows. We have already determined that the region in which the hinge K lies when the total range of movements of the actuators are used. The hinge K can never go outside this region consisting of four circular arcs. But L and K are 2 points on the same rigid body, so their distance cannot change. If the lip is kept fixed at L, then I rotate this line LK2 to reach the boundary of this region, that is K3, and this angle gives the angle of rotation that the bin undergoes keeping the lip at L. It cannot rotate any further because then K will go outside this range, which is not possible for the range of movement of the actuators which are given. Let me now summarize what we have learned today. Today we have solved three rather intricate, or I would say more advanced problems of displacement analysis of planar mechanisms through examples. Two having more than 1 degree of freedom, that is that front end loader and the earth moving machinery, and the other is a 3R1P non-Grashof linkage. What we have seen that this graphical method is very powerful, and clever use of the tracing paper as an overlay can become very handy to solve even more complicated problems of displacement analysis. In our next lecture, we shall discuss the analytical method of displacement analysis.